So the plan for today is having one more example from causality using in the gravitational setting, and then to move to analyticity properties and see how these constraints from causality gets imprinted in properties of the amplitude. So let's see where we finish this. So the example I want to discuss is the following. So the theory where I take gravity plus electromagnetism. So these are two massless particles, the gravitons, the photons, and so the effective theory is going to be the kinetic term for the photon, the Eiger derivative terms, the photon square with some coefficient here. Then I have the part which belongs to the gravitational sector, alpha 3 and to the 4th Riemann cube. I can be more explicit. Well, maybe not. So some contractions of Riemann here. Then there's a mixed term, for example, I'm going to write this in this form. In this one I can be explicit. And so on. And then there are other terms. And I want to discuss whether we can say something about causality, about the size of this term. The same logic that I'm going to show you is going to tell you something about the size of this coupling, but since it's a little bit harder here, I will focus on this example, which is simpler. Let me maybe just I think it's interesting to see what would be the expectation, how large beta can be naively. So let me show you that. So this amplitude here, this operator here contributes. So there are two amplitudes. So I'm scattering now to access this vertex. I need to scatter both gravitons and photons. So for example, if I scatter, let me simplify a little bit further. Not to have too many indices, I'm going to probe. I'm going to have a heavy source. Remember, the idea yesterday was to build some backgrounds where you see issue with causality. You propagate some signal superluminally. So I'm going to take the same strategy. So I'm going to add a source that produces some background. So I'm going to add, like for example, it could be a black hole, a source, a gravitational field. If we source this guy, it will give a correction to F squared. Okay. So a black hole seen from far away, that's what I'm going to do. Black hole seen from far away looks like a dot. So it's going to be like a point particle from the point of view of long distance physics. So the way I'm going to represent it is through adding a scalar field that interacts gravitationally. Okay, so basically I'm adding a minimal coupling here. I'm adding this guy. Okay, this is a simplification. Just say that it's a valid one. So I'm representing something that I cannot resolve the structure of the object. It's not spinning, so as a scalar field. So I'm going to look at the following setup. I'm scattering a scalar field that interacts gravitationally. You source some gravitational background. I'm going to scatter against the photon. Maybe 2 lines for the graviton, 1 line for the photon. And this interaction here is of the 2 types, right? There is this vertex here. That's one type. And there is also the minimal coupling here, right? The minimal coupling contributes to the helicity preserving process. The all incoming momenta will be plus minus. And the helicity, so this one is going to be proportional to 1. So you're following Alex's course. I'm going to write it in terms of spinors. So this is this. Which scale with energy just like E squared over m Planck squared. So as Alex was showing, this as momentum squared, so is twice, so it's momentum to the fourth divided by an energy square, so this is going to be energy squared divided by m Planck squared. And then there is this one that contributes instead to the Licity flipping process. It's going to be plus plus, for example, or minus minus. And it's going to be proportional to one insertion of this coupling. And it scales with the helicity in this way. Beta, I put it, there's S minus U square divided by T. And at a hand, so if all momenta are comparable, this goes like E. So basically, you can see it here. There's an M here, which I forgot to put. So it's going to be E M to the fourth times beta. M Planck, sorry, there is also an M Planck. So it's E to the 6, actually. So it's E to the, sorry, it's M square here, sorry. Nobody, it's M square, so square. So it's F4. E squared E over M Planck squared times beta. The typical size. So in principle, you could admit that beta is large because even when the energy is order or the cutoff of the theory, there's this factor that's suppressing it. As long as I'm adding, as long as the M is much more than M Planck, the amplitude will remain small. So in principle, beta could be large. However, if you do an NDA estimate, how large it can be, for example, you try to generate it by looping some fermions. So you need to generate an F here, which is scaling like a dA, another F here scaling like a dA, and you need a Riemann, which is a ddH. So this one is going to scale like E4K. Then you have 3 propagators. So if these are minimally coupled matter, you will get 1 over M Planck here, 1 over M Planck. This is 1 graviton. These are fermion minimally coupled to electromagnetics. You will get E squared, the coupling constant, and then there's a loop factor, the 16 pi square. Then, so the propagator I put it, then there is the vertex. There's this vertex coupled to the energy momentum tensor of the fermion. And that's it, I think. Yeah, I have to remove the 1, 2, 3, 4 momenta that I'm pulling out to select the right operator. So the Riemann is going to be proportional to dA square ddH. Okay, this is going to generate an operator that scales like this. So you see you have 6 powers here, 4 here. So this diverges the infrared like 1 over k squared. So it's cut off by the mass of these guys. So this one gives you E squared over 16 pi squared, 1 over M Planck, 1 over the mass of those particles. And then I have F mu squared. And then if I absorb M Planck inside H to go in the basis where Einstein-Hilbert is normalized in this way, an M Planck here, I reabsorb it in H. This one disappears, and you get two Fs and 1 Riemann. So the typical size that you would expect would be this. So if you compare it with this one, you see that you don't expect actually beta to be large. Sorry? This one? So this is a scattering of a photon against a neutral scalar. No, this one comes from beta. This one plus minus comes from here. The coupling of gravity. So every particle is a long distance coupled the same way to gravity. Everything follows the same, apples and planets. So photons as well. And is this vertex. Plus minus is the helicity preserving one. In fact, by the Coulomb principle is the same as minus plus. Both helicity fall the same under the gravitational pull of a scalar that generates a gravitational field. Now, instead, the Coulomb principle is broken by eigendimensional operators. For example, I'm adding here an operator that is generating a new vertex plus plus. So, for example, I send this is called sometimes called birefringence. I send a photon with certain polarization. There is a heavy source. It bends, so light bends, but it also change polarization. Okay, so this is a new physics effect. It doesn't come from Einstein-Hilbert. Doesn't come from neural coupling to gravity, but coupling comes from the higher dimensional operator. And the question we're asking is, how large can this be consistent with causality? That's the Gedanken experiment we are going to run. But before running it, I wanted to show you that beta could, in principle, be large from the point of view of having a small amplitude. That's consistent with beta being large because you have a large suppression due to one Planck. Gravity is very weak. So even you can allow to add something big here because it's still going to be suppressed by a Planck. But in fact, if you do an estimate of how large it can be, you don't expect it actually to be much larger than one. However, this argument, if you think about it, is only show you that if you take it large, it's going to be okay because it's going to be normalized by a small amount. It stays large. So it would be a problem if you had put it too small relative to that amount. Then that would be inconsistent with the RG. Okay, with this, with this consideration, let's run our Gedanken experiment. So we have a scalar that generates a gravitational field. We're going to have this photon travel across the gravitational field and see whether it travels superluminally. And I will need to solve geodesic equation of photon in this background, which is doable, but I can simplify my life a little bit by boosting the black hole more and more and reducing its mass at the same time, such to keep the energy fixed. I said, so when I boost, the energy goes up with the gamma factor, but if I reduce the mass at the same time, I keep the energy fixed. Okay? In the limit where I have a very boosted object, the metric degenerates to the following. Generated by the source is going to be null coordinates in light cone coordinates. It's going to be this. Delta U. Which is called a shockwave background. So you take the singular limit you're taking a black hole background, Schwarzschild. You boost it at the same time you lower the mass. You go from Schwarzschild metric to this one, to the shockwave background, which is a solution of Einstein's equation, where you put matter which has only one component, which is the following, the TUU component, which is localized on a word line. Basically, the picture is the following. So yeah, U, V, your light cone coordinates. You have a transverse plane. You have a particle traveling. So There's a delta function of u. So u equals 0 is this plane here, presented here. So if this one wasn't there, so away from u equals 0, this is flat space-time. So before this plane here, before reaching u0, so for u negative, is Minkowski. For u positive, is again Minkowski. Everything is happening on this surface, u equals 0 surface, okay, which is labeled by the other coordinates, x perpendicular and v. So v is drawn here, x perp here is the toggle direction that I cannot draw because it has to go out of the blackboard here. So, and you see the only source that generates this is a particle moving here. And there's a particle boosted, and the only thing to infinite limit and send the mass to 0 is a massless particle with infinite energy, with finite energy, that generates this shock. And now I want to send a photon. Okay, that yeah, it's. Maybe try to draw it. There's a third axis here, right? The x perp. So you draw. I send a photon. You hit here somewhere some impact parameter b, distance from the shock, from the source of the shock. And then we will see we'll gain some time delay. Go up here and then keep going like this. Or if it was no shock, it would just go straight like this, 45 degrees. Instead, here before the shock is Minkowski, 45 degrees. Before the shock is again Minkowski, 45 degrees. But everything, the dynamics is happening only on this surface. So where it gets a jump, it gets a kick in this direction, as we would say it. So this is the background I'm going to use to run the causality argument. It's the shock wave background. The solutions of Einstein's equation under this matter content. So a massless particle moving in the v direction. Something very physical. Okay, maybe let me tell you also, the only question is what is this delta here? You have to solve the Einstein's equation, you have to put these metrics in Einstein's equation, you get that the only non-trivial condition is that the two-dimensional derivative square here on delta is equal to E, the energy of the particle, I call it EA, the energy of this particle, I call it A, divided by m plus square times delta 2 x perpendicular. So it's a Poisson equation in 2 dimensions. Electrostatic equation, basically, but in 2 dimensions. Not surprised because everything is happening on a plane, right? So the whole dynamics that knows this is happening on the plane, so that's why you get everything is 2-dimensional. It's also very physical. If you think about it, you have a field, a Schwarzschild black hole at rest. Yes, so field lines are all radial, and now you're boosting. You have Lorentz contraction. All the fields get squashed. They all go infinite boost. They get squashed all on the plane, and the interaction becomes instantaneous like this. The same happens also in QED, by the way. Take the infinite limit of a charged particle, infinite boost of a charged particle. We get a pure gauge here, pure gauge there, and everything happening also in a plane. So let's keep determining it. So we are in the process of building a background. Right? Remember, that's what we are trying to do here at the moment. Try to build a solutions of these equations upon which I'm going to try to see if there is a pathology with a large beta. Now, we haven't finished because I haven't solved yet the equation for the background. So I need to determine what delta here is. I have the differential equation that determines it. So do you know what the solution of this is? From electromagnetism class. So basically, what's the Green's function of the Laplacian, the 2-dimensional Laplacian? Well, it's going to be the Fourier transform Sorry? One? 1 byte? Can you say louder? So we are in two dimensions. So if you Fourier transform it, this equation will look like this, right? It will look Q, Fourier transform Q squared equal 1 equal EA over M Planck square, right? So perp. So if I Fourier transform back, I solve this. So it's an inverse Fourier transform. E to the minus Q perp x perp 1 over Q square EA over. Now dimensional analysis d2k over Q square. Which function is going to give me here? A log. Indeed, it's log divergent. This is going to be a log of x perp. So it's invariant of the rotation, so it's going to be the modulus. It's going to be a minus, it's going to be an IR cutoff. And then EA over M Planck square. So now everything is determined. Notice there's an infrared divergence, however. It's a bit annoying. It's not too important. You need to regulate long distance physics. For example, embedding this in ADS. So if you add, rather than working in Minkowski, you deform a little bit this. Basically you change this a little bit. Here you change here plus lambda. Lambda will be very small. Arbitrarily small is going to produce a curvature radius. It's going to show up here. Okay. As long as our experiment is on a scale much smaller than the scale of the curvature radius, we can neglect it. Just enter here to regulate this divergence. Okay, so this is the background we are going to work with. So let's see how a photon travels on this background. So let's solve this equation. Right, the geodesic equation for a photon, null trajectory. At fixed impact parameter. So I fix x. So let's fix impact parameter is going to be a some distance from the source. So I have a source, it's generating a plane where it lives, and I have my photon coming with some impact parameter, some distance here. Okay, this is going to keep it fixed. It's going to be this one. So the metric, this part I can drop, traveling with this constant. The only part that matters is this one and this one. So the equation is going to be du dv equal du square delta u delta of b, my impact parameter x perp fixed. So I get dv du equal delta u to b. I get a differential equation for how v is going to change when it crosses the shock. So when you are away before the surface of the shock, this is 0, so just 0. So it travels a constant v. So it travels a v constant. So this is v. So constant v travels like this. However, if you integrate this in a small minus epsilon plus epsilon minus epsilon times epsilon around u equals 0, it gets a jump because there is a delta function that doesn't vanish when I shrink epsilon to 0. That's precisely this jump here I was alluding to. The change goes to V constant, hit the shock, get a delta V here, it jumps. The variation delta V is going to be equal to delta B. So the variation, it gets delayed. So this is a light cone. If there was no background, relative to Minkowski, it would travel like this, straight, kind of straight. Instead, the trajectory it does is the following. So it travels straight. It gets delayed by delta V equal this function here that we determined, this one, evaluated at the impact parameter, equal to that delta evaluated at x perp equal B. Okay. Depending on the distance between the particles. So there's a particle generated a shock, this surface here. Okay. I'm arriving. With the distance relative to the particle, it gets kicked a certain amount. And you see that I go inside. Or if I draw the light cone, I get delayed by an amount delta V. So bottom line here is that if I keep, not for now, without having put beta in the story yet, where is white? I get the delta, the time delay here, the variation of time delay is equal to delta V. It's equal, well, proportional because I didn't follow too much order one numbers to delta B. Delta evaluated x perp equal B, which is equal to minus EA m Planck squared log of B over the size of the universe. Or the box, much larger box where I'm running the experiment. So this is positive. Okay? The impact parameter is smaller than the IR cutoff. The energy is positive. So minus times a negative log is positive. So that actually is a way to, yeah. So this is just to say that gravity delays you. So it just doesn't give you any time advance. In a sense, we could have predicted this without doing any calculation, just by dimension analysis. So remember, we started saying there is a black hole, a rest, watch it, then we boost it to produce this metric. So what is the relevant scale for a black hole? It is Schwarzschild radius. So it's clear that, which is G times M, basically. Okay? Scale with G times M. So that's the only scale. So the time delay when you travel here a black hole is going to be of this size. Now we are boosting it. We're going to get a gamma factor, but we are extending the mass to 0 to keep this fixed, to keep the energy fixed. That's precisely what we got. Right? Here. Here. Okay. It's no surprise. There's only a scale for black hole, it's Schwarzschild radius, so better be proportional to that. And so this was without including a correction to the geodesic equation coming from beta. Okay. So what is going to happen if we add beta? So I'm going to calculate time delay. And so in order to determine it, so okay, let me be, so you have to solve, okay, let me maybe say the following. The same calculation here, I did it, so here I presented like solving a geodesic equation. An alternative way of doing it would be to solving equations of motion for the field. If you solve this, plug in here this metric, and you get the You solve it, you get exactly the same conclusion. Right? No surprise. Solving a system travels superluminally. This is the equation for a photon. So now if you turn down beta, what you need to do is to solve a similar equation. And this will modify the time delay depending on the polarization that you're going to put here. This one, the result doesn't depend on the polarization. Every polarization falls the same way because the equivalence principle. But since you're adding higher dimension operator, you get a correction. So you get the same EA m plus squared times log B over infrared plus minus beta over m squared beta squared. So I'm not showing you how to do calculations. It will be solving this. Okay, but it takes it's not something I can do at the blackboard. It takes a reasonable effort. But you can guess it by dimensional analysis. You need to adding something linear in beta over m squared is linear. It's going to be linear in G Newton, so in 1 over m plus square. It enters the factors already, so which I already pulled out. It must be proportional to the energy of the source. So this is the only thing it can possibly be. It has to decay with distance because I'm adding an irrelevant operator. The longer, the farther I take the source from my photon, the smaller this effect has to be. So you could have guessed it basically just by dimensional analysis. So you work one day, try to solve this equation, and basically to figure out which number you get here. You get 1, okay, which is a nice, comforting number. But so how large can beta be now? So now we built a background. We found a solution on this background. The photons travel straight until it hit the shock wave. It gets delayed, and it keeps going straight, except now we are adding an higher dimensional operator. So depending on the polarization I'm sending now, can get a little bit less delayed, right? So this is delayed by the same amount, both. Then some polarization is more delayed than the other. Okay. And if beta is very large, so suppose this, let's make this assumption we want to falsify. Let's suppose beta is very large. Then I can take B much smaller than M, so, sorry, B much smaller than 1 over M. Sorry, much larger than 1 over M. So within the regime of validity of the theory. So long distance. So distance is much larger than the microscopic scale of the theory. So where this is small, but beta is large enough that makes this larger than this one. So in that case, whatever sign beta I had, I can choose one of the polarization in order to dominate over this leading contribution. So I find a contradiction. So if beta is too large, there would exist a regime within EFT where I will get time advance. Delta T will be negative. For a suitable polarization depending on the sign that beta had. Okay? So this is another way to show. Therefore, you don't want this, so you have to discard this hypothesis. Beta cannot be too large. Is it clear? In a sense, yeah, I think this formula here is very simple in a sense. It is proportional to the mass But the energy is source gravity, so it's proportional to the source, the coupling of gravity. Energy divided by Planck square. Then there's the leading contribution that gives you time delay. Now, if you're allowed to add an eigendimensional operator, which comes with a large coefficient, yes, this decays for large B. If this coefficient is large, then I can be, still this one can be a small number, but if this is bigger than that, I can get some time advance. So that's not possible. So this implies that beta must be smaller. It's at most order 1. Questions? Well, once it's boosted, it's not. There is something called Lorentz contraction. Well, because you're boosting one direction. And there's a let me see if I have any intuition to tell you.
For the boost, your black hole.
Spheric. Yeah, sure. Yeah. How many of you knew about this solution of GR? I mean, it's very simple. Either way, you can just take this as a metric, plug it in Einstein's equation, and find what T would give rise to that. So you see that this T, so it's a particle that has traveled luminally, localized in Y and Z. The point particles travel at the speed of light with the energy E finite. Perfectly sensible metric. Is the metric, so a black hole at rest gives you Schwarzschild. A photon gives you a shock wave. Photon traveling has energy, the form of space-time, the metric you get is a shock wave. Okay. So I wanted to add something maybe to the discussion, which I didn't prepare, but talking to Alex, I thought it would be interesting to mention. There's another way to think about this problem, which in terms of S matrix directly. I want to mention that. It's very useful when you do these calculations. So you see, everything is happening at this plane. So before hitting the plane, nothing's happened. And nothing. So its dynamic is as simple as it can possibly be. It cannot be simpler than this. Nothing happened, nothing happens. Instantaneous, something happened. Just solve some boundary condition. So that means that if you try to calculate an S matrix, so what can possibly be? So you are calculating K, some momentum outgoing, overlap with some momentum P incoming. Now, basically, there is a preferred slice of space-time where you quantize. You quantize. So you fix initial data some time slice like this one, a null surface. Then you evolve it in time like this until you swap all space-time. This was done for the first time by Weinberg in a beautiful paper in the 60s called Physics at Infinite Momentum. Beautiful paper. So the idea is that when you have a particle that's, when there's something that's very energetic, everything is localized in a plane, so it's convenient to slice the space-time with planes. So you're asking, if I give you some initial condition here, some momenta even here, I try to evolve them in the future. And it's clear the simple way to do it would be to do the path integral. Because nothing happens from here until you hit the surface. Right? So it's very simple. You insert a complete set of states here. So So you insert a complete set of states, for example, before hitting the surface, 0 minus. This is your S matrix element, right? Insert a complete set of states, localize on the surface, so you have to integrate over the other coordinates, because you're doing the path integral, so it's coordinate dv and d to x perp, and insert a complete set of states. Now this part here is simple, right? This one. It's simple because it's happening before hitting the shock. Before hitting the shock is a free theory. There's nothing happening. So this is just e to the minus px, this guy. This one is complicated because it's x before hitting the shock, k out, k after. But I can set another complete set of states here, the one at u past the shock. So it'll be dv to x perp, dv prime dy perp. So this is the integral of the surface coordinate just a little bit past u equals 0 of k out y u equals 0 plus y u equals 0 plus x at u equals 0 minus x p in and this u equals 0 minus. Now everything in this expression is known. So you are propagating, so you have a free wave, you have a plane wave before hitting the shock. This is e to the minus px. Now you have this one is after the shock is again a plane wave, and with the coordinates after just after the shock, there's nothing happening again. So this again is e to the I ky, and everything, all the dynamics is specified by this. And we solved this problem. This is just setting what's happening at the shock. It's just going to be the x perp is the same as y perp, and 2, and v prime is going to be v minus delta of x perp. Is the thing that we determine. Then you just after the shock, you are delayed relative to where you hit. So you hit the shock here, you are delayed by some amount, delta, that depends where your transverse coordinate, which is what I've written here. So this is a very simple integral now. So I have integrations by delta functions. So this one gives you 2 pi delta. So if you go, so it's better to go in null coordinates for this exponential. So if you do it, you get energy conservation delta function times an integration e to the minus. So the energy conservation of the particle traveling the shock. Then you have integral d2x perp on the transverse direction. And then you get e to the minus the energy of the particles times delta of x perp. This is just this. So for example, what integration in y gets removed by the delta function. Integration in v sets the v inside here equal to the v, which is here up to a delta, and that gives you this factor. The e to the p v minus kv with the same v integrated in v gives you this factor, and k perp here is the difference between k perp minus p perp. So it's the momentum exchange. Since we know delta, we just solve the problem. So we know the S matrix in this theory. The S matrix in this theory is the Fourier transform of this exponential. It depends on the impact parameter. So set the other way around. If I Fourier transform the S matrix with the inverse transform, I go in what is called impact parameter basis. The impact parameter basis Fourier transform my S, the S matrix, with inverse. This is called S matrix in the impact parameter space. It's typically represented like this with some scattering phase, which depends on the impact parameter, and we just solved it. It's equal to this factor. So delta, this scattering phase, is the energy of the particle times delta, which is written somewhere. It was the time delay anyway, so it was proportional to delta V. It was proportional to the time delay. So said differently, if you know the scattering phase, take the derivative with respect to PV, equals 0, you're going to get the time delay. So that's a way to, from amplitude perspective, how to calculate the time delay. Rather than going through solving Einstein's equations, you rather calculate the scattering phase by calculating Feynman diagrams. Calculate this by Fourier transforming the amplitude. Take a derivative with respect to the energy of the particle, this is going to give you the time delay. So you need to calculate this diagram. I wrote it before, now I erased it, but in terms of spinor, that's what I started at the very beginning, tell you what this is. If I was to Fourier transform this, actually it's very simple to see perhaps. This one is proportional to 1 over T. It's a T-channel pole here. This is proportional to the momentum exchange. So the 2D Fourier transform of that is precisely the log of B. You see, I'm reproducing all details of the Einstein's equation just by doing a Fourier transform of a simple pole. Adding beta here is just changing this interaction a little bit. So it's going to change the Fourier transform a little bit. The net result is that it changed the time delay by an amount proportional to beta the way I was showing. Okay. Questions? So I think this derivation for the S matrix is new, just I derived it yesterday. But the first one who derived it, I think, is Toft in another way, in this way, with the geometric picture, in 89. And it's a beautiful paper, which I recommend to read. I think this way is actually pretty straightforward. The insight after many years, I think there's a simple way to do it. Questions? This shows, again, there's a connection. If you want, this is a preview. I just was telling you that you can build backgrounds where you can test superluminality. And asking not to have it is constraints of the coefficients. And I just derived a connection between the time delay and S matrix elements, right? I just calculated. If you calculate an S matrix element, take it with respect to the energy, it gives you the time delay. If you require this is positive, it's going to give you a constraint on the amplitudes. See, this is not what people usually refer as positivity bound, but it's another one. It's another form of it. Okay? This idea here of using the impact, the scattering phase in order to calculate the time delay, I mean, it's very old. It goes all the way back to Wigner, and has been used in gravity to bound, for example, this operator by in a paper by maybe almost 80 years ago, I guess, by Zhibuedov, Maldacena, Camaneo, Eden, and others. There are no questions. I move on to the other topic I wanted to cover today. How much time I have? Yeah, I think I want to use them. Yeah. The ones I will never finish. But don't be shy. I mean, I'm trying to show you things which I think are cool. So that because you need to like the things you do research, and to motivate you to look in them more. And in my notes, there will be much more details than what I presented here. So don't be scared. Yeah. But also don't be shy. So if you want to ask questions, no problem. Okay, so I want to discuss the following now. Subluminality implying microcausality. Then, if there is time, on the LSG formula plus microcausality, so therefore that's subluminality. Implying analyticity or scattering amplitudes. Okay, so this is the thing I want to show you. So let's start from actually classical subluminality implies microcausality. So let me show you what I mean. So take a classical field theory for a scalar field for simplicity. Okay, and you give some initial condition. You try to solve the equations of motion. You give initial condition of some time slice T0. So the solution, so that these initial conditions are pi and phi and phi dot. You give in each position, so at phi at T0, in each point of space, it gets some configuration. Right? This is your initial condition for the position. And then for its momentum conjugate, general would be pi. If you have a theory with more derivative, it would not be phi dot. But so let's try to be simple case. Then you have to give what is the derivative also in any point, right? There's a second order differential equation. You give the initial condition, then you evolve it in time. From T0, you try to evolve it to another time. So the solution, solving equations of motion, are going to be some functional of the initial conditions. Right? Solve the differential equation as a function of the initial conditions, and you get some solution. Now, subluminality is the following statement: that on the time slice T0, time. Sorry, this is x. T equal T0 is the T equal T0 line. This one. You give some initial condition in a region. You draw the region that it could be affected by changing these initial conditions. So at later times, if you change the initial conditions here, nothing of the solution has to change in this region here. That's the subluminality condition I'm going to impose. That you can, if you flip, you say, well, I don't want to have this one, but I want to have twice that, but only in this region. The thing that should change is only inside the light cone. Okay, you cannot reach this point, for example, if I change it only in this region. Okay, so this condition is nothing but the following: the variation of the solution with respect to the variation of the initial conditions at 0 if the points are space-like separated. And likewise, the variation of the solution relative to the phi dot at 0 if the points are space-like separated. It must hold for any size of A here and dilate for a point. Okay, so this is subluminarity condition. So it's my assumption. I'm assuming that the theory doesn't propagate information outside the light cone, is this condition, in the classical limit. So I can rewrite this. Now let's do the step to quantum mechanics. So this one, actually this one can be rewritten in terms of Poisson brackets. And this one, sorry, with phi. This one, Poisson brackets with phi dot. So we are saying subluminality is this condition, but if you want to be fancy, you say, well, it's a Poisson bracket of 5 and the initial condition at 0, a space-like separation. The Poisson bracket of 5 with itself at a given time, a space-like separation, has to vanish. And now you are perfect position to go quantum. Right? What is the quantum rule? You take observables in classical physics, which have a certain Poisson bracket, and you replace it with the commutators multiplied by I h bar, right? Put a nice hat on it. So we just derived that by canonical quantization, a space-like separation. Okay. So subluminarity plus canonical quantization, microcausality. That's, by the way, why it's called microcausality. Why we call it, why the vanishing of the commutator, you would call it causality. This is why. How much time I have? -1. Okay, maybe I will not have the time to discuss this now, but let me maybe just say the following. That let me just say the following. So, second step I want to show you is that we establish that subluminarity implies microcausality. Now I want to use microcausality in the LSD reduction formula to show that the amplitude is analytic in the variables. So the strategy is the following. So you write the LSD formula. It's a sort of a projector. So it takes some correlator. So suppose, okay, let me be step by step. So suppose you want to calculate 1, 2, going to 3, 4, in, out. Okay, connected, removing the identity part. And so this one you can write it in the following way. So yeah, like this. You can write it as 3 T phi 1, and then have a LSD prescription for particle 2 and 4, which is multiplied by box plus m squared for particle 2, box plus m1 for particle 4, do a Fourier transform with a suitable sign of the exponential, and take the limit on shell where P2 squared goes to M2 squared, and P4 squared goes to M4 squared. That gives you this. So by L at Z, I mean all of this. Multiply by this, take it for a transform, pick the right sign, go on shell. So this is what I mean by this operation. Operation acting on this object. Now, this is not in the suitable form, because we would like to use that the commutator vanish as space-like separation. So let's rewrite it in terms of commutators. We use the following identity. The time order of two operators of any type, just an identity. Okay, let me write it maybe this way. Be useful tomorrow. Call it Jx, J dagger 0. Can be written as step function 0, the commutator of Jx, J dagger 0, plus the error I'm doing, plus J dagger 0, J of x. So this one is an identity, okay? So it's just true fact, right? Because the T ordering has two step functions. One is provided by this term here. Right? When this is switched, there is a step function here. Is, if you want, there's a 1 here, which I can write as theta x0 plus theta of minus x0. Okay, write that way. So if you write that way, it's immediate. So you plug that here, you will see that this part survives, remains after L at Z reduction, but this part here drops. This is under L at Z. So if we do L at Z 2, 4 of this, which is in our case would be box of P or box or M2 square, box M4 square acting on these operators, would be box M2 square acting on phi is this one. I have another one. This one is going to give me 0. So this part doesn't contribute when you apply LSD. So I can equally use the time order version, or for our purposes, it's better to use the commutator version. And the reason why this vanishes is very simple. Instability of this part here, insert a complete set of states here. So in a sense, this LSD is just saying this produces a particle 4 in the outgoing state. So let's write. So this is this amplitude here. This contribution here will be proportional to the amplitude for 4. Then if I insert a complete set of states here, it will be 4 going to anything. And so let me I have sorry, I have 1. So this is sandwich. Sorry, this is a sandwich between 1 and 3. So what I'm getting here is 1 going to 4 plus n states will be this part, and this other part will give you m for n states plus 2 going to 3. That will be proportional to that contribution, sum over the phase space of m particles produced. And particle is stable, this matrix element vanish. Particle 3 is stable, this matrix element vanish. So that's why the stability of the particles that forbids this process. So you can equally work with the time order, or you can work with the commutator. When you apply for LHC purposes. In fact, the LSD paper, the original paper, wasn't this one. It was actually with the commutator. The second paper, they say, okay, actually, you can use this one. Okay, I think I'm way over time. So let's leave it like this. So we are gonna, here we create a link between superluminarity and microcausality. And what I show you here is that I can put the commutator as part of the definition of the S matrix element. So what I'm gonna do tomorrow is to show you that because commutators, so I can basically replace this with a commutator and with a step function. Because there is a commutator here that has to vanish a specialized separation, and because there is a step function, this formula is going to tell you that this amplitude, there's an equal sign, the left-hand side must therefore be analytic in the momentum. Okay? And then we will use analyticity to prove various type of positivity. Questions?